imagine opening multiple apps on your phone, WhatsApp, YouTube, or Chrome, all running smoothly at the same time. Have you ever wondered how your system manages all of this without crashing? So that's where process management in operating systems comes in. Hey everyone, I am Manthan Sharma, and today I will break down this concept in the simplest way possible, with examples you actually understand. So let's dive in. So first of all, let's understand what is an operating system. An operating system is not just a software. It's like a manager of entire computer systems. It handles CPU, brain of computer, memory, RAM, and devices like keyboard, disk, etc. The input-output devices. But here the key part is it doesn't just run one program at a time. Instead, it manages multiple processes simultaneously. For example, when you are watching YouTube and downloading a file at the same time, the OS is deciding which app gets the CPU and how long it runs and when to switch it. So, this decision making is called process management, and without it, multitasking would not be possible. So, the next topic is the process concept. So, let's go deeper. A program sitting on your disk is just inactive code, but the moment you run it, it becomes a process, meaning it starts using CPU, it gets memory, and it performs tasks. So think of it like this: the recipe is a program, and the cooking is the process. So a process has multiple parts like code, stack, heap, registers. So the code text is an instruction of in text format. The stacks has the function calls. The heap is a dynamic memory, and the registers are the current CPU state. So all of this together makes a process a living entity inside the system. So let's understand about the process states with real life flow. Okay. So now processes don't run continuously. They keep changing states. Let's understand with this with a real example. So when you open an app, it starts in new, moves to ready, and then it is running, which means executing. So if it needs data from disk, it goes to waiting. Once done, it becomes terminated. So it's like a cycle: ready, running, waiting, ready, terminated, then new, ready, running, and waiting, and then terminated. So the OS constantly tracks these movements to keep everything efficient. Now let's understand about the PCB. So now imagine handling hundreds of processes. How does the OS remember everything? So that's where PCB, process control blocks, comes in. Think of PCB as a file or record for each process. It stores process ID, current state, CPU registers values, or memory details. So here's the important concept. When CPU switches tasks, it saves current processes data in PCB. So this process is called context switching. When CPU switches tasks, it saves current processes data in PCB. This is called context switching. So without PCB, multitasking simply wouldn't work. Now moving on to the scheduling part or the process scheduling. Now, so who gets the CPU or for how much time? So this is decided by the process scheduling. There are three schedulers: long term, short term, and medium term. The long term decides which process enters the system. The short term picks next process to run and run very fast in milliseconds. The medium term is temporarily remove process or swapping, which you can call swapping. It temporarily remove processes from memory to reduce load and reintroduce them later. So think of it like college admission is a long term, class teacher is short term, and setting arrangement is medium term. So each plays a different role in managing system. Now moving on to the scheduling algorithm. So now how does the OS decide priority? So using scheduling algorithms like FCFS, SJF, priority scheduling, and the round robin method. So in FCFC, first come first serve, it is a simple queue. So the first process comes, it runs, and then after it the second process which comes, it runs. So it is like whoever first comes will get the running time. Okay. So the problem in this is it is very long waiting time. It is very long waiting time because the second process also waits for the first to complete first. So it takes so much time. Then comes the second one, shortest job first. So it picks the process with the least burst time, and it is optimal in theories, but also it requires prediction burst time. So it is best performance, but hard to predict. Okay. Then comes the priority scheduling. It runs the important tasks first. So the risk is low priority task may start. So the risk of this process that if a low priority task is given, it may start. It may wait for long period of time. And round robin, which is the most important scheduling, each program gets equal time slice. For example, process runs for 10 milliseconds, then the next process runs. So this ensures fairness and it is widely used in real systems. Now moving on to the operations on processes. So processes are not static; they are created and destroyed. So process creation. A process creates another process, parents to child. For example, opening a new tab. The second is termination. When process finishes execution, OS frees the memory and deletes it. Then comes the context switching. So CPU switches between processes. The OS saves the current PCB and loads the next. Okay. So too many switches can reduce performance. Now moving on to the IPC. Now let's talk about the interaction between the processes. Some processes are independent or cooperation. Independent means no interaction with anything, and cooperation means sharing data. For cooperation, we use IPC. So there are two main methods: shared memory and message passing. So in shared memory, it is fast. Processes access the same memory and need synchronization. In message passing, it is safer. Process send, receive messages, and is slightly slower. For example, browser tabs communicating with server is an IPC in action. So without IPC, modern apps wouldn't work. So one important issue in IPC is race condition. When multiple processes access data at the same time, it is called race condition. So when processes wait forever, it creates a deadlock. So that's why the synchronization is very important part in IPC. So the conclusion of whatever we learned today. So let's quickly revise it. So process is a program in execution. PCB stores the process info. Scheduling is the CPU decision making, and the IPC is communication between processes. So from smartphones to cloud servers, everything depends on process management. It truly is the backbone of the modern computing. So guys, if this made things clear for you, hit the like button. And if you are preparing for exams or interview, subscribe for more simple explanations like this. See you in the next video. Keep learning.